This is part 3 of my sequence on chemical thermodynamics, and specifically we're going to look at the Gibbs Free Energy calculations. You'll recall that thermodynamics deals with the study of the energy changes that accompany physical and chemical changes in matter, respecting the 4 laws, the 0th law about heat flow, conservation of energy, the increasing of entropy, and the finding that entropy at 0 Kelvin is 0. Now let's talk about the Gibbs Free Energy, or delta G. It's a mathematical predictor of whether a chemical change is favored or not. Now, delta S, total delta S, is equal to delta S of the system minus delta H over T, which of course is the delta S for the environment or surroundings. If we multiply all the terms of this relationship by negative T, we get negative T times the change in S, delta S, is equal to delta H minus T times delta S of the system. If we define delta G, the Gibbs free energy, as minus T times the change in entropy for the total system and environment, then we get the equation delta G equals delta H minus T delta S. This is the change in Gibbs free energy. So we have the equation on the top here in the bar, and this is a state function, isn't it? G is equal to enthalpy minus Ts. So delta G is equal to delta H minus T delta S if the temperature remains constant. If pressure and temperature are constant, the sign of delta G tells us about whether a reaction is favored or not. If delta G is 0, the reaction is at equilibrium. If delta G is positive, the reaction in the forward direction is not favored. Therefore, you have to supply work to the system to make it happen at all. If delta G is negative, the reaction in the forward direction is favored. The higher the delta G in terms of the absolute value, the more it goes in the forward direction. So if you had a delta G that was minus 2,000 joules, then it's going to be more likely to go to completion than if it was maybe minus 100 joules. Now, what physical quantity does the Gibbs free energy represent? It is the maximum energy released during a thermodynamically favored process that you could turn into work. It's the energy available from a thermodynamically favored process that could be used to drive a non-thermodynamically favored process. Typically in biochemical reactions, ATP-producing reactions are favored. For instance, the oxidation of glucose. That produces ATP, and the reaction itself is thermodynamically favored because the delta H's are negative and the entropy changes are generally positive. Those ATP-producing reactions then give you ATP that is used to drive ATP-consuming reactions. And that really is the thermodynamics of biochemistry right there. Now, delta G is a state function that we can look up as delta G standard in tables, and that's given at 298 K, which is about room temperature. Standard values for delta G imply a standard state in which they are measured, so we have to be aware of what those standard states are. For solids, the standard state is a pure solid. For liquids, the standard state is the pure liquid. For gases, the pressure is at 1 atmosphere, and for solutions, the concentration is 1 mole per liter, or 1 millimole per milliliter. For elements in their normal state, delta G of formation is defined as 0, and that gives us our 0 point for the measurement of delta G. If we know delta G of formation, we can tell whether a mixture of chemicals will produce products or we regress to reactants. For example, what's the standard free energy change for the formation of ammonia at 298 Kelvin? There is the chemical reaction that you should already be familiar with. Delta G0 is therefore 2 times the delta G of ammonia, the product, minus the sum of 3 times the delta G of hydrogen and 1 times the delta G of nitrogen. Oh, that's actually pretty easy, isn't it? Because these two terms are 0 if they're in their standard state, which is a gas. So 2 times minus 16.66 kilojoules per mole is minus 33.32 kilojoules per mole. That's the standard delta G for the formation of ammonia at 298 K. The reaction goes spontaneously, that is, the reaction is favored, but at an unknown rate. Now, if delta G is equal to delta H minus T delta S, then the favored or non-favored status of a reaction depends on the absolute temperature. When delta S is greater than 0, we have increasing disorder, increasing the temperature merely increases the products that are formed. When delta S is less than 0, increasing the temperature will make the reaction move more to the formation of reactants. It'll cause the reactants to move more from right to left. Alright, when delta H and minus T delta S are opposite in sign, raising or lowering the temperature can make a big difference in the equilibrium values of the reactants and products. And now let's look and see the various combinations. If delta H is negative and delta S is positive, then both of these terms contribute negatively to delta G. Delta G then will always be negative. The reaction will be favored from left to right. And the more delta G is negative, the more favored it is, the more products you'll get. Explosions and fires have negative enthalpy changes and positive entropy changes, and so they fit in this category. When delta H is positive, here, endothermic, and delta S is negative, moving towards more order, delta G will be positive at all temperatures, and the reaction will go spontaneously, that is, it'll be favored right to left. Products then will be small or non-existent, and reactants will remain after the chemical change is finished. Example, biosynthesis. Putting biological molecules together always requires energy and always reduces entropy. If delta H is positive and delta S is positive, then delta G will be dependent on the temperatures. The reaction will reach an equilibrium state, and the temperature is going to determine what K is. And of course you knew that. Now you know why temperature determines the equilibrium state. If delta H is negative and delta S is negative, then delta G will be dependent on temperatures, just as the previous slide. The reaction will also reach an equilibrium state, and the temperature will have an impact on K, the equilibrium constant. So let's do a problem. For a given process, delta H is 53 kilojoules and delta S is 115 joules per Kelvin. The question is the process favored at 25 Celsius? Is it favored at 250 Celsius? So we calculate delta G. That's delta H minus T delta S. And at 298 K, delta G is 53 kilojoules minus 298 times 115, or 19 kilojoules. Positive. Therefore, this is not favored. But at 523 Kelvin, delta G, the same delta H, but now we have increased the negative value, the negative component of the equation, and now we're at negative 7 kilojoules delta G, and it is slightly favored. Note that at 461 Kelvin, delta G is 0, and this process would be at equilibrium. Reactants and products would be forming at the same rate. Note here that both delta H and delta S in the given of the problem are positive numbers. So we would expect an equilibrium to happen. Now the free energy and the equilibrium constant. This is very, very brief because you don't have to do any math. We can relate the free energy change at standard conditions and those at any other conditions. Delta G is equal to delta G0 plus RT times the natural log of Q. R and T are the usual. Q is the reaction quotient, product of products divided by product of reactants raised to their coefficient powers. So we can change this equation to KEQ is equal to E to the negative delta G0 divided by R times T. This is something that you will see in physical chemistry in college and will be very useful at that point. For now, you need to understand the relationship between the delta G at any temperature and delta G0 and the equilibrium Q. This math is not subject to testing in the current version of the AP test.